So Mary and I are going to talk about why functional programming matters. And I want to kick off by talking about functional programming a la 1940s. So back then, functional programming was pretty minimalist. So, think of Booleans, for example. Who needs them? All you do with Booleans is make a choice, right? Well, we can do that with functions. So why don't we define functions true and false? And we'll let them make choices. To make a choice, you've got to have two things to choose between, so let's give them two arguments each, and say, well, true will choose the first one, false will choose the second one. So there we are. Now, instead of Booleans, we can use these two functions. Or can we? Well, if I'm going to be able to use these functions instead of Booleans, I need to be able to implement if then else. And I can do that. How can I define if then else to take a Boolean and choose the then branch if it's true and the else branch if it's false? Well, I could just call the Boolean and let the function make the choice. So that's great. I don't actually need Booleans. I can use functions instead. And, well, while we're at it, what about integers? I mean, what are integers for? Positive integers. Except counting loops. So why don't we do away with integers and instead use functions that just iterate a loop? So we'll define 2, for example, to take a loop body f and a starting value x and just iterate f twice. And 1 will call f once and 0 0 times and so on. And obviously, for any integer now, any positive integer, I can think of a function that iterates a loop body that many times. And if I want to, I can even take one of these functions and recover a normal integer just by iterating a loop body that increments a normal integer and starting from the normal integer 0. So if I take 2 and I iterate the increment function twice, well, I convert it to 2, of course. So that's great. So I can take any integer and represent it as a function this way, but that's only fun if I can do things with them. Can I, for example, add them together? Oh, well, hey, if I want to iterate f m plus n times, I can do that first of all by iterating f n times and then m times on the result. That's m plus n. Great. So I can add two integers together. I can multiply integers by nesting loops. If I want to iterate f m times n times, then I can just use an outer loop that iterates m times, and in the loop body, I'll iterate f n times. That's m times n in total. So I can multiply these things. Does it work? Well, let's add 1 to 2 times 2. That should be 5, right? If I construct 5 as a function, and then I iterate the increment function 5 times from 0, I get 5. Wonderful. Now there's no stopping me. Look, here's factorial a la 1940. And I'm just using my simulated Booleans and my simulated integers. So if I'm given n and it's 0, then I'll choose 1. Otherwise, I'll multiply m by the factorial of decrement n. There's not a real integer or Boolean in sight here. It's all functions. Does it work? Well, let's take the factorial of 5 and use that once more to iterate increment from 0. Yes, we get 120. It all works. Well, there's a couple of functions here I haven't defined. I've got to define a 0 test. That's easy. How do you tell whether one of these functions represents 0? You just iterate a loop body that returns false, starting from true. So then, if you iterate it 0 times, you get true. Anything else, you get false. And I also need to be able to decrement one of these numbers. And the less said about that, the better. But you can do it. And so, what do we get here? Well, we see that Booleans and integers, they're unnecessary. We can do everything with functions instead. And actually, the same idea applies to other data structures like, pairs, products, sum types, you name it. Any ordinary data structure you can replace entirely by functions. So who wrote this code? Alonzo Church. These are Church encodings, and it's more than just a theoretical curiosity. Early versions of the Glasgow Haskell compiler actually implemented data structures this way. Not integers, of course, that would be crazy. But the other data structures, it turned out there was a time before pipelines were so deep when this was the fastest way to implement data structures in Haskell. So that's kind of cool. Before you try it, some of you I'm sure will want to try this at home, so let me just make a confession. If you do, you'll get an error message from the type checker. And it says, okay, cannot construct the infinite type, blah. Well, constructing infinite type sounds difficult, of course. And don't worry, you get more information to help you debug it. The Haskell type checker will tell you which type it was expecting and which type you gave it. And in other news, this is the first time I've used a 3-point font on a slide. So I appreciate it's a bit daunting to try and figure out what's wrong from this error message. But don't worry, there's more. And you can perhaps guess from this that this isn't the kind of programming that Haskell is most commonly used to do. In fact, you need to give the type checker a little bit of help. You need to add one line to the code I've shown you, which is to tell it what the type for factorial is. And the red bit here is what the type checker can't infer for itself, and it's just telling the type checker what the type of a church numeral is. Apart from that, you can do it. So the amazing thing is that Church could write this kind of code without being able to debug it on a computer. But 20 years later, you could run this kind of code on a computer, thanks to John McCarthy and Lisp. And that is the factorial function in the first version of Lisp. Right from the start, the very first Lisp paper also talks about higher order functions, so you could map the factorial function down a list of integers. So functions as data was important right from the start. Map list is what we call map today. And Lisp got a lot of people very excited, including this guy, Peter Landin, who in '65 wrote a paper about the next 700 programming languages. In the abstract of the paper, he says, today, 1,700 special programming languages are in use. There were 1,700 programming languages already in 1965. That's kind of a horrifying thought. But Peter Landin thought, well, if there are only 700 different application areas, let's have one language to rule them all with 700 different libraries. That was his idea, really. Anyway, there's the factorial function in ISWIM, his language. But what I want to emphasize is not really the language, but another idea that Peter Landin really, really stressed in this paper. And that was the importance of laws about programs. So what do I mean by a law? Well, here's a law about Lisp programs, which says that if you reverse a list and then map a function over it, you'll get the same result as if you map the function over the list and then reverse it. And that's nearly true. It's nearly true because, of course, those two programs on each side of that equivalence will perform the calls to F in a different order. So if F has side effects, then it won't be true. But, you know, it's quite a good law even so. So Landin was a firm believer in laws which were not nearly true, but true, always and absolutely. And he even has a little discussion in his paper when he thinks the reader might doubt that. The reader might look at an equation like this and say, what's the point of having two different ways of doing the same thing? Wouldn't it be better if the two sides did something different? Then you'd have two facilities instead of just one. And Landin thunders, no, expressive power should be by design rather than by accident. I'm right, you're wrong. I love that. I mean, you can't disagree with it, can you?
And continuing on from giants, when John and I had a little bit of marital strife about what to talk about in this paper, but there was one paper that we could just agree from the beginning must be mentioned in this talk, and it is Bacchus's Turing Award paper, the paper related to his Turing Award in 1977, called Can Programming Be Liberated from the von Neumann Style, a Functional Style and its Algebra of Programs? This was a hugely influential paper because Bacchus was a giant among ordinary programming language people. He had developed Fortran, made a fantastic Fortran compiler, and he had also developed ways to describe programming languages. So he was somebody with weight. And he wrote a paper. Now, he got the Turing Award for all that in 1977, and he could have written a paper wallowing in the great things that he had done. But he didn't do that. He wrote a paper that was another manifesto for functional programming. And if you haven't read this paper, you should do so. It is an amazing paper. The first sentence of the abstract is this: conventional programming languages are growing ever more enormous but not stronger. And the rest of the abstract goes on to list the defects that Backus saw in the conventional programming languages of the day. So the next sentence is, inherent defects at the most basic level cause them to be both fat and weak. In this talk, we're going to concentrate on 3 of those defects and his solutions for those defects. And then they're going to appear again and again. The first defect that he points out already in the abstract is what he calls these programming languages primitive word-at-a-time style of programming inherited from their common ancestor, the von Neumann machine. So this paper is the one that coined the term the von Neumann bottleneck, and Backus explains that a computer has a CPU and a store and a thin connection between the two, and you have to pass words back and forth across this connection. And this influences our way of doing programming. And one of the theses of the paper is the von Neumann way of designing machines also had terrible effects on how we write programs. And he wanted to find a new way of writing programs, not by thinking word at a time to go through the bottleneck, but by thinking about whole values. And that's a theme that will come back again and again in the talk. So that was the first defect, word at a time. The second defect he points out is their inability to effectively use powerful combining forms to build larger programs from smaller programs. So that was the second one. What did he mean by combining forms? Well, he meant higher order functions, what we would call today higher order functions. I'm going to visualize a couple of them. Now, I'm going to visualize them making use of Backus's way of defining function composition. So I'm going to visualize programs as blocks where data flows in and out of the blocks, and the data is going to flow from right to left because of the direction of his function composition. So this is a kind of apply to all. Take a function and apply to all elements of a vector. He called that alpha. This is what he called construction, which was to take a bunch of functions and apply those functions each to a single input to produce, so for 4 functions, we'll produce a vector of 4 outputs. Construction. So and composition, again, was another of his combining forms, so we could compose a map with a construction, for instance. So that was the second defect, that normal programming languages didn't have these ways of building small programs from large programs from smaller programs. Defect number 2. Defect number 3 was their lack of useful mathematical properties for reasoning about programs. So this is the third important defect. So he wanted to develop combining forms and study the laws that those combining forms obeyed as a way to assist the process of developing programs. Let's look at a couple of these laws. So if we take a construction and compose it with a function, that will be a construction of f1 to fn composed with g. That should have the same behavior as if we move that function along those inputs, and so that the function reappears at the input of each of these colored functions. So this collection of functions should have the same behavior as the previous one. And so and this is described as a construction of f1 composed with g, f2 composed with g, and so on. So we should have a law relating those 2 programs. So that was his first example of an algebraic law. And the second one was, if we have a map composed with a construction, or if we have this arrangement of functions, we can actually divide it up in 2 different ways. We can describe it as a map composed with a construction, or we can divide it up in the other direction and describe it as a construction of f composed with g1, f composed with g2, and so on. So this is an example of a law which is, here are 2 different ways to describe the same arrangement of functions. So these are the first 2 algebraic laws that Backus lists in his Turing Award paper. And then he has a whole bunch of other laws about his other combining forms. And he gives a very small his first program that he shows is inner product. He starts by showing it in a Fortran-like language. So we're going to assign C to be 0, and then we're going to have a for loop which gradually builds up the result of taking the inner product of A and B. And he spends about half a page taking this program apart and saying, this is dreadful. We don't want to think words at a time, and the things we need to think about are spread out in the program, and this is not how we want to write programs. We don't want to have to algorithmically, sequentially say how to make the result. We would like to give a kind of denotation of the result. And this is his inner product program. We read from the right. We take our pair of vectors, we transpose it, we apply to all of multiplication, and then we compose insert plus between all the resulting values, or fold plus, we perhaps would say now, or reduce plus. And then he borrowed from APL and introduced APL-like notation for many of his combining forms. And this might have been a mistake. So we have trans composed with apply to all of multiplication composed with insert a plus for our inner product. And what I'm going to do next is not continue talking about what is in the rest of Bacchus' paper, but I'm going to move on to another paper that I see as a kind of Bacchus paper light. This is functional geometry. So I arrived in Oxford in 1980, and Peter Henderson, who wrote this paper, was my supervisor. And when I arrived in Oxford, he was having fantastic fun with bits of tracing paper and drawing lines and drawing pictures of fish and trying to figure how they fitted together in order to construct Escher's square limit fish picture. And he wrote a paper about that that appeared in 1982. And what he did was he studied the ways to combine small pictures to make larger pictures. And so he builds the entire square limit picture out of a single fish. Here's our initial fish. What we're going to do is develop a set of combining forms that allow us to rotate it and flip it and then plug them all together to make the final square limit. So we can compose two fishes by overlaying our first fish with a rotation of that original fish. That's two fishes. We can compose three fishes by overlaying the first fish with two other versions of fish, fish 2 and fish 3, which are defined in terms of rotation by 45 degrees with flip or 3 rotations. So now we have a 1 fish, we have a 2 fish, and we have a 3 fish. And you can see that Escher was quite clever in his way of designing the blocks, the subparts of his picture, because they all fit together very beautifully. We can also fit together 4 fishes by overlaying the original fish, a rotation, 1 rotation, 2 rotations, and 3 rotations of the original fish. And it still all fits beautifully together. And then we begin to think of, so now we have 1, 2, 3, and 4 fish, and we need to think of how do we plug together larger collections of them. So Peter introduces above and beside for composing pictures, and then quartet, which allows you to compose 4 pictures without any overlaying now, but beside and above. And then cycle allows you to compose 4 copies of the same picture, but rotated as you go around. And with that, we can make cycle of rotate of our 3 fish, and then a quartet of that. And we're getting somewhere now. We're getting closer to what the square limit looked like. This is a good middle of the picture. And the next part of the paper figures out how to make the sides, how to add some stuff on the top, on the edges. So if we take quartet of nil, nil, rotate of our 3 fish and our 3 fish, we get that. And then we take quartet of that twice. So that is, we take 2 copies of that on top of itself. This all still fits together. So that will make a fairly decent side. And then he considers how to make the corners of the picture. And again, he uses some quartets. And he introduces a sequence of corners that add smaller and smaller parts along the edge of the corner. And finally, he takes 9 different pictures and puts them together, a nonette instead of a quartet. So we have the corner rotated in all once, twice, 3, and 3 times. We have the side rotated 3 times, and we have U, our original middle, in the middle. And we're done. So this is a denotational description of the square limit picture. But Peter had another trick up his sleeve. And that was, so you might have imagined that he would just have a data structure for these pictures and then he would walk over them somehow and draw the picture. But no, he has pictures as functions. So the pictures as function theme continues. So a picture is going to be a function from 3 vectors to whatever you need to produce to draw the picture. So, and the 3 functions are going to point to the origin, the kind of bottom of the picture on the left. They could be parallelograms, but we're going to have them as rectangles here. And once you've made that decision that a picture is going to be a function, it becomes very easy to define what these combining forms are. So over of P and Q applied to its 3 vectors, well, it's just going to be P applied to its 3 vectors and Q applied to the same 3 vectors. And that's going to produce all the lines that you need to produce to draw the picture in the same triple of vectors. Similarly, we can define beside for A, B, and C as P at vectors A, B over 2, and C, and Q at vectors A plus B over 2, B over 2, and C. And rotation. If we want to rotate the picture that has 3 vectors A, B, and C, then we just need to move the origin over to that corner. So that's A plus B. And then its next vector is going to be C, and its third vector is going to be minus B. And we need a way to produce pictures from our basic pictures as well. So he needed a way to produce a picture of the original fish. And in designing this set of combining forms for pictures, Peter was very concerned about the laws that they should obey. So here's an example of one of the laws. Rotate of above on P and Q is the same as beside of rotate of P and rotate of Q. And he remarked that, having listed the laws of his combining forms, it seems there is a positive correlation between the simplicity of the rules and the quality of the algebra as a descriptive tool. And so this is an example of laws as a litmus test in your design of your combining forms. And so we've seen, the reason I call it Bacchus Light is that we've seen all of the ideas from the 3 defects and their solutions from Bacchus's paper reappear again. We have whole values, we're talking about whole pictures, we have combining forms, and we have algebraic laws as a litmus test for your design of your combining forms. And Peter has added one extra thing, which is functions as representations, because he has pictures as functions. And at the very end of the paper, he sums up what is the important idea in this paper. He says, the basic idea exemplified in this paper is simple. Denotations of objects are easier to understand than algorithmic descriptions of how to build those objects. So Peter's paper is a manifesto for thinking about how to describe things denotationally. And if you want to play with functional geometry and pictures, one way to go is to look at work by Connell Elliott, who has taken this denotational approach to the very limit and worked about and done beautiful work about functional image synthesis. It's called PAN, and you can go away and play with it. And it's got lots of very mind-bending pictures that you can also look at.
Okay, so we're going to skip ahead a little bit in time. I just want to tell a story that I like very much from the mid-90s. So at that time, DARPA had a big project that they were running in software prototyping. And at that time, you couldn't get money from DARPA to work on developing Haskell as a real programming language. But Paul Hudak got money to work on Haskell as a prototyping language. There's nothing to be ashamed of in that. Haskell was in here along with other well-known prototyping languages like Ada and C++. But they got the money from this anyway. And partway through the project, DARPA decided that they would run an experiment to evaluate how good these various languages were at prototyping. And Mark Jones got the job of solving the problem that DARPA posed, constructing the prototype for comparison with these other languages. So DARPA being DARPA, it was a rather military kind of application, the two-dimensional geoserver. So you were given positions and tracks of ships and aircraft, and you were supposed to classify regions of 2D space into areas with strange names like weapon doctrine and slave doctrine and tight zone, this being DARPA. And so Mark began to prototype this, and you were supposed to produce output that would say, at time 40, the commercial aircraft will be here, in the engageability zone, in the tight zone, the hostile craft will be somewhere else, and so on. So Mark started prototyping this, and the first thing he decided was he had to represent regions in the plane, and why not use functions for that? So a region will just be a function from a point to a Boolean. It's true if the point is in the region, and false if it's not. And he started defining some simple regions, like a circle with a given radius is really easy to define. The outside of a region, well, you just negate the Boolean. That's dead easy. The intersection of two regions. The point is in the intersection if it's in the first and it's in the second. So you just conjoin the two Booleans. Some very simple primitives, and then he could go on to define an annulus, that's the ring shape that was in the diagram, which is just the outside of one circle intersected with the inside of the next. And so on, and he built the prototype. And when the results were compared, Mark's Haskell solution was 85 lines of code. It was the shortest of all of the solutions that were submitted, and it was an order of magnitude smaller than the prototypes in Ada or C++. So when DARPA got this, they basically didn't believe it. They thought, well, yes, but if you use Mark Jones to build your prototype, then no wonder you get a small solution. It's also, by the way, it's got the most documentation and one of the shortest development times. So DARPA said, okay, without telling Paul or Mark, they picked a graduate student somewhere else. And they said, okay, you've got 8 days to learn Haskell. Go away and solve the problem. And that graduate student solution is the second shortest. The annoying thing here is the result could have been even better because Mark had put in 29 lines that the type checker would have inferred for him. So it could have been 56 lines of code there. So you would think, okay, this is a great success. Haskell has been very successful. So what did the evaluators say? Too cute for its own good. Higher order functions are just a trick, probably not useful in other contexts. If Church had been dead, I'm sure he would have turned in his grave. Anyway, going backwards in time again a little bit now. In 1976, there was 2 papers that described different aspects of a new discovery, lazy evaluation. Henderson and Morris wrote a paper on a lazy evaluator, and Friedman and Wise wrote a paper called Con Should Not Evaluate Its Arguments, which were both, they're both credited with the invention of lazy evaluation. And that's really significant for the themes we're describing because it means that the whole value that we keep talking about can actually be infinite. For example, you can have a value that is the infinite list of all natural numbers. Or I started off talking about using functions to iterate a loop body. Well, now we can iterate f every possible number of times. We have an infinite list of all of those iterations. And you don't fall into an infinite loop because when you write this code, it doesn't mean that you will compute infinitely many elements. It means the consumer gets to decide how many elements will be computed. That's the key idea of lazy evaluation. So what you're writing here is code which can produce arbitrarily many list elements, but the consumer decides how many you want. And I saw this and I thought, oh gosh, that'd be great for numerical algorithms, which I'd always had trouble writing. So here's a consumer function that you might use in numerical methods. You give it an infinite list of approximations that are converging to the correct value, and we'll just pick the first one that's within epsilon of its predecessor. So we just keep going until it converges. And if you write this limit function, and then you use lazy infinite lists of approximations, you can write numerical algorithms very, very prettily. Here's the Newton-Raphson square root function, for example. So you compute one approximation from the previous one with this next function that you see there. And if we just iterate that, starting from any value really, I've picked 1, and then wait until it converges, you get the square root. Here's how you might compute a derivative. So to compute a derivative of a function at a point x, well, you take x at a point close to it, and you compute the slope of a little line segment between those 2 points. And then the gap, h, is something that as you make it smaller and smaller and smaller, so the value you get converges to the true value of the derivative. So here I'm just making a list of h's that's getting smaller by halving at each step, using each one to compute the slope, and then taking the limit in the same way. And what you see here is that the convergence check is the same in each case. It's reused. I only have to write it once, but I'm using different approximation sequences. And once you start programming in this way, you can take it even further. So differentiation is done by taking 2 nearby points and computing a slope, but you integrate in a similar kind of way. You can use the Trapezium Rule, where you add up the areas of a lot of thin rectangles. Let's call that width h as well. Now, the key thing here is that in both cases, the smaller you make h, the better the approximation you get. And it turns out that whenever you're using a method like this that's based on some parameter h that's getting smaller, what you get is the right answer, let's call it a, plus an error term, which is approximately something times a power of h. So now, if you take 2 successive approximations, right, we know n, we know h, we know these 2 values, and there's 2 unknowns, a and b. Remember school mathematics? You can solve for a, but a is the right answer. So if you've got a sequence of approximations, you can just take the first 2 of them and solve and get the right answer. You don't need to bother with the rest. Well, that's not quite true. Actually, what you get here, it may be a better approximation than many of these, but it's still an approximation. However, if you take the following 2, which are a little bit more accurate, and do the same thing, you'll get an even better approximation, and so on. So you can use this trick and just solve for a at each step, and you get another sequence that converges much faster. What you've done is you've eliminated 1 error term from the method. And once you can do that, you can do it again. Look, here's a really, really fast derivative. First of all, we'll make the sequence of approximations with a simple method, and then let me eliminate 2 error terms. That gives me a sequence that converges at lightning speed, and I'll just take the limit using the same convergence check that I used before. And so I really love this. Everything is programmed separately. It's easy to understand. And it's thanks to this whole value programming, where we manipulate the whole value, the whole sequence of approximations in one go. So these are some of the key examples in my old paper, Why Functional Programming Matters. They're an instance of lazy producer-consumer. So if you have a producer and a consumer, and you don't use lazy evaluation, one of the things that can happen is that the producer can run ahead and keep going faster than the consumer can keep up. With lazy evaluation, then the consumer demands each element, and the producer produces one at a time, which also means that when the consumer has seen enough, the whole process stops. And I've just talked about using this, where the producer is producing numerical approximations, and the consumer is the convergence test. But there are many other ways you can use the same idea. Another way that I used it in the paper is when the producer constructs a whole search space as the value. And the consumer is the search strategy that selects a value you want from it. In the paper, the search space was a search space for a simple game, noughts and crosses. And the consumer was alpha-beta search. But today I want to talk about another paper that uses the same idea, where I designed a pretty printing library in '95, and here the search space is all of the different ways to lay out something that you want to pretty print. All of the different valid ways of laying something out. And the consumer is the selection criterion for the best layout. Okay, so what does a pretty printer do? Well, it makes choices the whole time between alternative layouts. If you are printing an if-then-else, for example, if everything is short, you might print it on one line. If it's a bit bigger, you might print it across several. So a pretty printer constantly has to choose between a horizontal form and a vertical form. And in the vertical form, you can see here that there's some indentation. But of course, you don't want that to appear in the horizontal form. So you're making this horizontal-vertical choice the whole time and putting indentation in as appropriate. So how can we do that? Well, we want to work with whole values. The values in this case were little fragments of layout, potentially with some indentation attached. And you can put these fragments together vertically, in which case the layout is preserved. You get a bigger piece of layout. And we write that as A above B above C. Or you can put them together horizontally, in which case the indentation gets discarded. And I wrote that as A beside B beside C. And if you think about it, okay, and we also need to be able to construct these little atomic bits of layout. And there's a function text that converts a string to a little piece of layout, and a function nest that adds some indentation. So looking at these, you can see immediately that there must be some laws that they satisfy. I said we discard indentation in the horizontal form. So if I put A beside something nested, well, that must be the same as throwing away the indentation and just putting A beside B. Of course, we don't throw it away at the beginning of the line. So if A is nested, then that's the same as actually putting A beside B and then indenting the whole combination with the indentation that A had. So here are two laws that should hold about these functions. Once you start thinking about them, there are many more. So when you put three things together horizontally, it shouldn't matter how you bracket it. And if you look at the picture and just imagine constructing it either way, you see you should get the same result. Likewise vertically. And even when you combine them. So if you put A above B and put that beside C, you get the same thing as if you put A above B beside C. And that's because putting things together horizontally in this library puts C beside the last line of B. So you're kind of putting them together like that. But it's not true that if you put A beside B above C, you get the same layout as if you put A beside B above C. Because when you put B above C, that fixes their layout relative to each other. So on the right, C gets indented, and on the left, it doesn't. So you've got an interesting set of laws here. Many things are true, one or two things aren't. We need one more function to write pretty printers, and that's the function that makes a choice between horizontal layout and vertical layout. So set is just going to say, I might be horizontal, I might be vertical. This is a slight simplification, but that's basically it. And now it's really easy to write pretty printers. Here's a pretty printer for a Haskell tree type of binary trees. So we just have a case that says if it's a leaf, we build a string and convert that to a layout. If it's a branch, it might be laid out horizontally or vertically. So if it fits on one line, it'll be horizontal, otherwise we'll split it into a line with a branch on it, and then the indented left subtree and the indented right subtree with a closed bracket added at the end. That's all you have to write. And so as you can see, it's extremely simple. The implementation, though, has to figure out what layouts you might get. And what it does is it uses the laws behind the scenes to transform this into the best layout. And without thinking about the laws, I could not have written a correct implementation of this API. Or perhaps I should admit, before I thought of the laws, I wrote very many wrong implementations of the API. I just couldn't get it right. It's tricky. You need to understand how these things should behave. So then you need a heuristic as well. My heuristic was to limit the output to the maximum page width, of course, but then also limit the length of the text on each line. I think if you only have a one-line document, putting it all on one line just because it fits in 79 characters is not necessarily a good idea. It might be more readable to split it. So that was my heuristic. But because of this separation between the consumer and the producer, you can use the same API, the same pretty printers, with a different layout function to get alternative layouts. So I know this was a good idea because so many distinguished people have improved on it afterwards. And that's always a good sign. So I want to quickly mention one more thing. I'm probably best known nowadays for my work on QuickCheck, which Koen Claessen and I initially came up with it in 2000. What does it do if you haven't seen it? Well, you write down properties of your program. So here's a property in Erlang of the reverse function that says, for any list x's, if you reverse it twice, you get the same list back again. And then you can test that. And QuickCheck runs a lot of random tests and says, yes, it seems to be true. If you write a wrong property, then, like this one that says, if you reverse a list, you get the same list back again. Of course, that's not true. Then QuickCheck will first of all say, that's not true. Here's a counterexample. It's a randomly generated one, very hard to understand. But then it shrinks it down to a minimal counterexample, 0, 1, which is much easier to understand. Why is this minimal? Well, if you only have 0 or 1 elements in a list, reversing it does leave it unchanged. If you have 2 elements that are the same in a list, reversing it leaves it unchanged. So you need 2 elements, they have to be different. 0 and 1 are the smallest 2 different values, and so that's the smallest counterexample. So why mention it now? Because it's the same idea. What's happening is that a property describes the space of all possible tests. The consumer is QuickCheck, QuickCheck search strategy. But QuickCheck, first of all, does some random search, and then a systematic one to find the minimal counterexample. It's the same. It's whole value programming. The whole value is the property, and it makes QuickCheck really simple to use. Okay, I'm going to skip this in the interest of time. Mary.
Thank you. There was just a teaser, but I'm going on to the next slide. I want to return to pictures. Now, this is a book that appeared in 1980, the same year as I arrived in Oxford. And it was, Bacchus attempted to revolutionize programming. This book by Mead and Conway did revolutionize how we design circuits. Because this is a book that came out in 1980 and that opened VLSI design to ordinary people like computer scientists. And it has changed the way that hardware is designed. It has led to the foundation of companies like Intel and so on. But if you look at this is a VLSI circuit, it's not a million miles away from square limit, right? So if you can figure out how to draw square limit, you can probably also figure out how to draw these kind of circuits. So while Peter was having fun drawing fishes, I was having a lot of stress trying to draw real circuits. And we had a 4-pen plotter, and we used to go to the bottom of the PRG and watch the plotter drawing the circuits. And the reason why it's stressful is that if you get it wrong, if you, for example, connect your power wire to your ground wire, then you send it away to be fabricated, and you wait 9 months for the result to come back. So you have to get it right. So my first attempt to produce circuits was to use functional geometry directly to design circuits at this level, drawing each of the transistors and describing it. And that seemed like something we needed to improve on. So we need to add a programming language above that. And at that exactly the right time, Bacchus's paper appeared and told us how to describe regular things. So one of the themes in the Mead and Conway book is we should describe circuits as regular structures of small cells. That's how we should do it. And Bacchus's paper could be seen as an explanation of how to describe things that are regular structures of small cells. So I wanted to think about in what way do Bacchus's laws help us in the process of designing circuits. So here's an example. If you have an orange circuit and you know how to push two blue circles through it and have the blue circle remain, then it is also the case that if you have a kind of block that looks like this with one of these inserts or reduce at the bottom, then you can gradually push pairs of blue circles through so that you end up with something that looks like this. So, and that has the same behavior as the previous circuit. So if these orange circles, for example, are registers, then what you're thinking about here are pipelining of circuits. So what I did was take FP, Bacchus's FP, and turn it into a language which describes plugging together streaming functions. And then it's possible to apply laws like this. So what you're going to do is you can, if you wish, replace a block of circles composed with a reduction by, a triangle of circles composed with the reduction of something which is the composition of a square circuit and a circle. And this is exactly the kind of reasoning that our industrial partners at that time, Plessey, were looking for. So they came to the PRG and they wanted to talk to people about designing circuits. And of course, I, as the doctoral student, was wheeled out to talk to them. And they had, of course, read Mead and Conway too, and they were trying to design regular array circuits. And they were having trouble with their regular arrays. So what they were doing was drawing the circuits on large pieces of graph paper in a room, and then they were walking around on the graph paper in order to try to figure out whether data would meet at the right places in the circuit. So what we did was provide them with a little implementation of MuFP and a symbolic simulator for that little programming language. And they were then able to use that to think about how data flows in their circuit and to experiment with different ways of doing things. And they wrote a nice paper about that, saying that using MuFP, the array processing element was described in just one line of code. MuFP had taken the APL approach to combinators. And the complete array required 4 lines of MuFP description. And MuFP enabled the effects of adding or moving data latches within the array to be assessed quickly. So having a language to describe what you're trying to think about gave a way to play with designs and to understand designs. They didn't then use the MuFP to generate the real circuit, but they described that separately. And that was nice. Unfortunately, our other industrial partner at that point bought Plessey and closed down the design team. So we did not go on to world domination. But we still continued to think about combining forms for describing circuits. I'm going to think about whole values. So we're going to think about inputs to circuits that are kind of arrays of values, which I'm going to think of as read with a column first. So first column, second column, and so on. If we want to take a function f and apply it to every second element of the array, we're going to call that ilv. 2 will be a function that applies f to the first half of the array and to the second half of the array. And if you think of a picture that looks like this, here's a law about 2 and ilv. 2 of ilv of f is the same as ilv of 2 of f. You can think of dividing this picture up in different ways. And once you have combining forms like 2 and ilv, you can begin to describe very regular structures. Here's an example of a regular structure, a so-called butterfly network. A butterfly network can be described as an interleave of 2 half-size butterfly networks composed with something which applies an f to each pair of its inputs. And we can draw it by unrolling the picture. So we have data flowing through on these wires, and these vertical things are the applications of f. And the interleaves produce these arrangement of wires. This might be a bit difficult to read, so there's a kind of standard notation. We can pull the wires so that the f's stretch and the wires remain horizontal. This is a picture of the recursive butterfly network. And the butterfly network is an important part of a famous sorting network by Batcher, called the Bionic sorting network. So he figured out that if you have a bitonic sequence, that is a sequence whose first half is increasing and second half is decreasing, and you push it through just the first part of such a butterfly network, you'll end up with 2 half-size bitonic sequences, and all of the elements of the top half will be greater than or equal to all of the elements of the next half. So if you keep pushing, you'll get from a bitonic sequence to a sorted sequence. So this is a merger. It merges 2 sorted sequences to produce a sorted sequence if these little f's are 2 sorters. And once you figured out how to make the merger, you can again figure out how to make a sorter, because what was a bitonic sequence? It was a sequence whose first half was sorted increasing and second half was sorted decreasing. How will we make a sorter? Use recursion. We'll sort the first half using S. We'll sort the second half using S, reverse the output, and put everything into the merger. So this is a doubly recursive sorting algorithm, which we can lay out in hardware or implement in software. And for 16 inputs, for instance, this network contains 80 of those two sorters. Backus invented another sorting algorithm called Backus odd-even merge. So the merger is defined using interleave again, but the final part of the circuit doesn't apply the F between the even pairs, but between the odd pairs, and passes the first and the last element through. So this is the odd-even merger, which can be used to make into a sorter. It turns out that that merger sorts a pair of sorted lists, or two sorted lists. And because of the use of the odds, which passes some values through, this has only 63 comparators for 16 inputs. It turns out, too, that there's lots of puzzles remaining about sorting networks. So having a language of combining forms to describe them can be very useful. If you want to try to design sorting networks, I can tell you that the best known 16-input sorting network has 60 comparators, and nobody understands it. And we don't know if we can do better or not. So there's lots of open questions. And following on from this obsession with combining forms, we made a library in Haskell called Lava, which you could view as a kind of functional geometry for circuits. It's based on exactly the same kinds of ideas. And indeed, there was a version of it that used functional geometry internally to give the programmer control over relative placement of the circuits. And at that time, Satnam Singh was employed at Xilinx, so we had a great cat and mouse game with Xilinx. So we would invent combining forms, lay them out with relative placement, get beautiful FPGA layouts like this, and then the Xilinx tools would try to lay out the same thing using simulated annealing or whatever, and we would end up with, spirals and all kinds of things. And they would improve their tools, and we think of more combining forms, and so on. And there have been many versions of Lava since then in various languages. There's one called Chisel currently in Scala, which you might like to play with if you want to play with designing circuits. And if you need a puzzle to keep you going during the rest of the day, you might not want to make a sorting network. You might want to make a network that takes an odd number of elements in and produces the median element at the middle output, but all the elements above it greater than or equal to, and all the elements below less than or equal to. So this, for example, is a 25 input median, which is an important function in, for example, image processing. This one has 96 comparators. The best kind of one that you can find in the literature has 99. And I published a paper where I was too embarrassed about the code that produced 96, so I showed the code that produced 98. But we don't know either how well we can do here. So there's plenty of opportunity for functional hacking and search and so on to try to improve on that. And I just want to say very briefly, you're probably thinking, oh, it's just puzzles, nothing to do with the real world. Well, even at Intel, there is use of functional programming in their verification. Now, if you're a company like Intel, you would like your processors to obey various useful laws. And in 1996, was it? There was the so-called Pentium law, where you got, n minus m times n over m equals, 256. And they took a $500 million loss because of this. They had to recall all the processors. And they became very interested in formal verification and hired all my friends. And the formal verification system that was developed from that time until now is called Forty. And it's based on a lazy functional programming language called FL. And it has thousands of users. So there's a quiet revolution in the use of functional programming that goes on in Intel behind closed doors. So it's a lazy functional language with built-in decision procedures and a symbolic simulator, like what we gave to the Plessy people long ago. And it's extremely cool. So they use the programming language for all kinds of things, from design language to specification language to implementation language for their improvers and so on. And there's another company that I will mention only briefly called BlueSpec. So you might also be thinking, oh, but VHDL and Verilog still dominate. So it's all very well that Intel are using a functional language behind closed doors for verification. But there is one company called BlueSpec that is pushing the idea of using a functional programming language to do hardware design. And they've taken some of the ideas that I've shown you about combining forms for describing circuits, and they've added another idea, which is to add the idea of guarded transition rules, guarded atomic transition rules. So you describe your architecture using the same kinds of combining forms, but you can also describe ways of dynamically using different parts of the architecture and so on. And it generates Verilog. And it's very explicitly about abandoning the sequential von Neumann legacy that we have. And it's also got a kind of secret weapon. And that is that there is a QuickCheck now associated with BlueSpec. It's called BlueCheck. And it allows users to write a synthesizable test bench. They just write their properties and they get checking a la QuickCheck. And this idea of a generic test bench is apparently blowing minds in the hardware community. And perhaps the coolest thing about this is that the shrinking that John talked about, and iterative deepening, can be implemented directly on the FPGA so that it will go very fast. So that people are generally using FPGAs to emulate circuits. And so they would like to be able to very quickly do quick checking of their circuits, and they can do that now using BlueSpec. So this is a very nice bringing together of ideas.
So we've talked about 4 key ideas: using functions as representations, programming with whole values rather than a word at a time, using powerful combining forms that obey simple laws. And those have recurred again and again throughout the talk. Functions as representations, that was Church. And the other 3 are in Backus's paper. So use these ideas, stand on the shoulders of giants. That's all we've got. Thank you.